Hi, my name's Danielle Vigent. I'm out here in Los Angeles, California. I have been inside of material handling and automation in the warehouse for 12 years now. Started off total warehouse, including conveyor systems and storage media and big integrated systems. And then slowly throughout my career, I've gotten more and more focused into industrial robotics. I also did tried my hand at making my own startup. It was a software as a service company trying to help food businesses be better. But I am back in the world of robots with Formic, which is doing robots as a service. And I'm having a really good time. I went to Cal Poly San Luis Obispo, got an engineering degree, and I've lived out here in Greater Southern California ever since.
Awesome. Well, thanks for meeting with me today, Danielle. And I wanted to pick your brain about robotic palletization. We get a lot of questions about it. Mm-hmm. And I thought, well, what better way to talk about this subject than with an actual expert that works with it day in and day out? So I got a couple of high level topics. I want to hit you with some questions. Some of them are softballs. Maybe some of them aren't. I don't know.
Great.
We'll just kind of work through it like that.
Joe and I have worked together at various companies in the past. We've actually done... Yes, we have worked together twice, actually, in the past. Let's see, I think you were my project manager for something.
Yep.
Long time ago. Yeah. And then we were colleagues. So we've known each other for 8-10 years.
Yeah, something like that. Yeah. We've done all kinds of wild stuff.
All sorts of wild stuff, but we've never lived in the same town.
The first big question is, what is a robotic palletizer? If you had 50 words or so, how would you describe it?
This is how I explain it to my friends who are non-technical, or like my mom. When they ask, they go, "Oh, you're an engineer. That's so great. What do you do?" I explain it to them as, in like a warehouse or a factory, you have to pick heavy things up and put them on a pallet. So bags, boxes, you name it. Pretty much it's just a big robotic arm. I usually make this little motion with my hand, like the claw, and it picks it up off a conveyor after it's fully done, and it puts it on a pallet, and then that pallet goes out into the world. That's typically how I explain it to random people I meet.
Okay. And then would you consider some other ancillary palletization or robotic palletization opportunities as pallet to pallet, conveyor to pallet, maybe robot to pallet? Are there some more exotic things that still fall into that category?
Oh, sure. I mean, you can really sort of, the world is your oyster, right? You can have multiple lines coming in, and multiple pallet build locations going out. You can depalletize things. So, right, if it's coming in on a pallet, you can take it off the pallet and put it on a conveyor line. You can have upstream automation, pick, pack, ship, like a pick module upstream coming down to a case. You absolutely can have a robot on a rail that's picking things up from various places and putting them on a pallet. You even can have robots picking up a single item and putting it to another outfeed. Just pretty much anything that a big giant arm in the sky could do, that's in the realm of robots.
Okay, cool. So what are the main components? Let's kind of talk about how does a palletizer work? What are the main pieces of anatomy of a system, like a robotic palletization system?
So first thing is you have to have a way to get it in there. Typically that's conveyor. I'm sure that I have done one application where it came in on sort of like a slide. So a non-powered conveyor. But typically it's going to be a conveyor on the infeed. So you got to have some way to get it inside of the cell. And then you have to have a robot arm. This part of things, physically moving, those things tend to be pretty large. They have some little small ones, but most of them tend to be, in the hundreds of pounds. And then you have to have an end of arm tool, which is kind of like the hand. This is the most custom part of things. You have a different end of arm tool or a different hand for every application. So it's going to look a little different if you're just doing 50-pound bags or if you're doing, 2-pound little cases. So you have to have an end of arm tool. Typically, you have to have some way to put things on a pallet. So sometimes that's as simple as we bend a piece of metal just like this and we slide a pallet up into it on the floor. and the robot can absolutely put things right there on the pallet. If we get a little more advanced, we can start doing some special handling. You can build a pallet on top of a conveyor so it can come in and out automatically, a little bit faster, a little bit more equipment. You can also get fancy and have a pallet dispenser. So you load up a big stack of pallets just like a Pez dispenser, and then when a pallet is needed, it just spits out a pallet and goes to where it needs to go. You can also get fancy and have a bottom sheet or slip sheet dispenser. You can have that be put just like a Pez machine right on that pallet, or usually the robot can actually go down to a magazine, have a little vacuum like nozzle, and then pick it up and put it on. So you can do some spicy things. You also need to have some safety. So sometimes we put a fence around it. Sometimes we do a fence and some light curtains. And with the fancy new collaborative robots, sometimes you don't need a fence at all. So that is sort of at bare minimum. There's a control panel, there's some electricity stuff, but pretty much get it in, get it out, have a robot arm, and have a way to control it.
Okay, cool. And then part of the anatomy that is maybe a little bit more invisible, but I think for folks like us, it's very much important, is like, how does it know where to go, and how important is presentation of the case or of the pallet, right? Because a couple of things you mentioned are actually like indexing mechanisms.
Sure.
Like, what does all that look like?
So most robots are blind. There are robots that have vision and cameras on them. They're typically a little bit more expensive, and they have a reason for that. But most palletizers are blind, meaning they don't have a camera, they can't see. But what they do know is X, Y, and Z coordinates. So when that case or that bag comes into that in-feed conveyor, typically what's going to happen is it's going to be justified to the same exact point, right? So it's always going to go, whether it's mechanically, we run the box up to a little T-stop, kind of like this.
In stops, yep.
Just boop, and it just goes right there. Then robot knows that's where it's supposed to be. There are a little bit more sophisticated ways. We can use lasers to justify things. It kind of depends on what the end of arm tool is doing, whether it's like a top-down vacuum or a clamp or a little combo of both. But we have to basically take the thing we're picking up to roughly the same spot in the universe, the XYZ, right? So because the robot's blind. So it's just going to blindly pick that thing up at the same place, and then also has to place it. So same thing, we want to make sure that that pallet is in the same spot in the XYZ world. And the robot has to also keep track of where it is on the pallet pattern. So it has to have a memory. It needs to have a recipe. It needs to have a layout of, okay, we have, 20 boxes, right? 4 this way, 5 that way. Where am I? Am I on layer 1, 2, 3, 4? So that part, the robot, again, it's blind. So it has to keep track of how it's stacking everything. So, like you were saying, Joe, getting that in, and justifying it correctly in a repeatable, robust fashion is pretty important. When in your world, does the sort of technology, is it also blind, or do you have to justify things in the same way, or kind of how does that work?
Yeah, unlike conventional conveyor systems, presentation is kind of everything, right? Like you need to make sure that when I enter a transfer or a divert, that I'm in a position that I can actually move the product in a positive method or way from there. So it is very important. Now there's some logistic circumstances where it just kind of, you can't do that. So I think you and I have also done a couple of bulk movement projects together. And it's just like this big fat conveyor, and it's just got random stuff in it. Right. Have you ever worked on any working from a random, I think you mentioned you had a slide, and that's a kind of an uncontrolled pickup point. Talk about that a little bit.
It was the slide. It was a semi-controlled pickup point. So it would come down, and it actually would hit a stop. We didn't have control over it left and right. But what we did is we used a clamping tool. So instead of coming down at the top, right? So if you imagine a big, those claws overhead for the game you play at the arcade.
Yeah, picks up the ball and you get a prize.
Exactly.
You always lose. Yeah.
So think of it kind of like that, but with better odds, because we're gonna pick it up every time. So because we couldn't control where the box is left and right, because it was a slide, right? It had some end stops, but it would move, 3-4 inches. We had an end of arm tool that was kind of a big claw, so it had lasers looking down inside of the slide. And when the lasers were cleared, right? So we knew it was in, roughly the center. The clamp tool would come down and it was bigger than the box and would kind of just go whoop and pick it up. So we had the ability to get a little bit, I don't want to say sloppy, but less precise.
You could compensate for that.
Yep.
that Y value that wasn't precise every time with like a larger, maybe more expensive like tool.
It was a more complicated, more expensive tool. The good news in that was we already had to kind of use that tool because the boxes were 50, 60 pounds. We start hitting the limit of what sort of off the shelf vacuum tools can do when you start getting that heavy. We like to start supporting it in a mechanical way instead of just relying on that vacuum for those big heavy boys.
It's like when you pick a trash bag up and the bottom falls out, right? You can do the same thing with a box.
Exactly.
Yeah, okay. That makes sense.
Yeah, that's precisely it. Once you start getting really heavy, like, we kind of want something underneath there or something, mechanically grabbing it. Not to say that vacuum, can't be used, but it depends. It puts a lot more onus on the box to be good. So anyways, we already had to use that clamp tool. So we're like, oh, this is fine. We have 3 inches of play on each side. It's no worries.
All right, cool. So like, is it generally true that like the more freedom you allow in that presentation, like the higher the cost is going to be for the solution?
There is a pretty linear correlation. Sort of the more variation and the more sort of complexity of how the item is presented in general, it's going to have some cost implications. So I always try to make it as simple as possible. How can we put a bent piece of metal at a precise position? There's, if you're breaking, steel, we've got bigger issues, but it doesn't require any maintenance. It's very, very affordable. It's very, very repeatable. So when I can get away with it, I try to just make it good old fashioned. You go up to a little end stop like this and your box, is justified. And, you got to powder coat a piece of steel and you're ready to go.
All right, cool. Yeah. Okay. Awesome. Let's also talk a little bit about, so right now we're talking about like one box. I take a box and I move it. I take another box and I move it. And I think this applies a little bit more to depalletization, but do you ever handle multiple units? And then what's the thought process there?
Yeah. So, there's some pros and cons. When you start handling multiple units, obviously you can go faster. If you're just like, at home, if you're picking up 2 things at once, it's, you're going twice as fast or, 3 times as fast. The cool news is you get a lot more rate for almost free, right? So you're moving the robot the same number of times, but you're now picking up 2 boxes, 3 boxes, 4 boxes.
It's almost free. So what's the cost?
It's almost free. So, if you're picking up 2 boxes, or 2 bags, that's more weight. So maybe that's inside of the robot arm payload, or maybe that pushes you to the next, bigger payload. So, the actual robot arm is larger. It's more expensive. Could be that. You also now have 2 sort of zones. So you have a larger end of arm tool, more money, more robust. It does take a little bit more complexity. And I say almost free because depending on how the pallet pattern is, sometimes they're really nice and easy where it's just, 4 boxes like this and then 4 more boxes like this. But sometimes, depending on if it's like interlocked or if it's a complicated pattern, sometimes it's 1 box like this and then another box 90 degrees this way and another box 90 degrees that way. So even if I'm picking up 2 at a time, depending on where I am in the pallet, that means I may have to take those 2 boxes. I have 2 phones here today. Look at that. I may have to take these 2 boxes, right? Drop one of them this way, pick it back up, and drop the other one that way. So, so you get that. It really depends on the pallet pattern and how fast you have to go. It also does require a little bit more complexity of the programming because again, yeah, like let's say, you have one this way, and then let's say the next box is actually the next layer. So it does require the robot cell to have the ability to drop one at a time sometimes. Some are very straightforward, just 2 by 2, and that's fine, but a little bit of variation. It's a pretty cool way to get more rate out of something without a whole lot more equipment.
Okay, very cool. Very cool.
Yeah.
And then you talked a little bit about like putting the robots in a cell and having a little safety around it, or a cobot, right? So a robot that an operator can safely like be around. And sometimes that would be desirable if I want to go and change out a pallet position because that one pallet's done being built. I want to put a new one in there versus having to put in a lot of like pretty intense pallet conveyor because sometimes it is a lot. So talk to me about like cobots and like what the trade-offs are with a traditional robot, and why I would or wouldn't want to, look at that for palletizing.
Yeah. So Joe, if you put yourself in the shoes of a customer, right? If I was to say, hey Joe, we're gonna make you a robot cell. I know that you've been in this plant in New Jersey for like 80 years, right? This is your great grandpa's pickle company. And you're like, yeah, we have, we are interested in putting a robot in, but we are really tight on space. And you're like, okay, cool. So what we can look to do is try to put a 2 pallet build location, something like 14 feet by 15 feet, something like that. And you might say like, oh, okay, we got enough space. There's a column there. Like, we can make it work. Everything's cool. And then I'm going to be like, Joe, we have to fence off pretty much the entire section except for where you're going in and out of the cell, where those pallets are coming in and out. And you might be like, oh, Danielle, that's not going to work. We have an operator that, he goes from the filler up to the palletizer, and there's no way for him to, get all the way around there.
It creates a monument, right?
Yes, it creates a huge monument, and it's visually very impactful. I always try to preface people to say, like, I'm going to be putting 6-foot tall fencing inside of your facility where there was nothing before. Your brain is going to have this moment every install. There's always this moment where the fence goes up and people are like, oh my gosh, it's so much bigger than I thought. And I'm like, actually, it's really not. But if you
it's
can
the same size. Yeah, it's the same size.
Imagine, like, if you can imagine you're in your living room and then all of a sudden, like, you get one of those privacy screens and you put it up in the corner, you're going to be like, wow, my living room looks so much smaller. And you're like, it's a 5 by 5 area, but like, yes, visually it's very difficult. So you have this game you have to play where traditional automation, we do the fencing and we do the light curtains, right? Sometimes some area scanners. It's very big. It's visually very big. It can have these big monument style flow disruptions, but they tend to be faster. So a traditional non-collaborative robot cell, the actual cell, the arm itself can move faster. The reason is there's a safety equation. It's a multivariable equation. It's like an OSHA rule. It's also from like the international, I have to look it up, the name. There's a multivariable equation that has a bunch of components. One of them is stoppage time, right? So like how fast the robot can react. One of them, multivariable equations, one of the variables is how fast the robot is going. Another one is like distance. And then there's a couple of other ways to make it up. So if your robot is moving quickly, right, it's just like a freight train, right? If you have a big, heavy thing moving quickly, it's going to stop slower than if you had that same
momentum,
thing.
Right?
Yeah. If you have that same thing moving slower. So our traditional automation, our non-collaborative robots, we throw a physical barrier, a fence around them. We throw some intelligent barriers, light curtains, area scanners, so that that robot can move as quickly as it can, knowing we have these barriers to entry. The collaborative robots, they can have smaller footprints, but the trade-off is, since we're not physically putting a barrier around them, the actual arms can move slower. So they simply cannot move in the XYZ like dimensions, like their speed is governed by that equation, right? So let's say it's same exact arm, right? No difference in mass. The cobots do tend to have slightly faster stopping times, but because I have to stay underneath an allowable sort of number, I cannot physically move that robot arm as fast. So we play this game where if you need to go very fast, I always try to recommend a non-collaborative cell because there are less sort of restrictions on the speed of the actual arm. If your rates, right, let's say upstream, you're like, Danielle, it doesn't matter. My pickle guys can only make pickles at 6 boxes a minute maximum. There is no way that the briner and the cucumber chopper, I'm just like fully making this up.
The black box pickle machine. Yeah,
right. There's no way that we can give you pickles faster than about 6 boxes a minute. It's impossible with the equipment we have. We're not going to upgrade for another, 20 years. I would say, what an interesting moment. It sounds like it might be okay to go to these slightly slower, in general, collaborative robots, knowing that it will be visually smaller, technically smaller, and we won't have to have the operators be so sort of removed from interacting with the cell. So it's what's that thing is like cheap, fast, and good. For robot cells, it's like cheap, fast, and and good, really. Or like how close you can get to it. You have to kind of play around and see, do we go down the traditional path? Do we go down the collaborative path? They are getting better. 5-ish years ago, 10-ish years ago, maybe 7 at this point, collaborative robots are really like coming into the market, and they were so slow, like painfully slow. The technology has I was like, they were so slow. The technology has gotten a lot better where they can stop faster, so they can actually move a little faster. But you're constantly pushing up against that, OSHA and robotics, I can't remember what the name, association formula. So just like everything, it's always a trade-off, right? And also there is one more factor. Sometimes, so whoever's doing the marketing for collaborative robots is crushing it. They are, whatever group of people are doing that, good job. Many small to medium businesses will see a collaborative robot at a trade show, on 60 Minutes, on some YouTube video, in a trade publication, wherever people are getting LinkedIn, wherever people are getting their media. Sometimes in family-owned businesses, or when you have like decision makers that are, not necessarily technical or things like that, they will get this idea in their head that a collaborative robot is the only thing that they ever want. And so you do have to wrestle with that, because the marketing conceptually is very, very good. You're like, yeah, I can have this robot right next to this guy. It won't kill him in theory. Put it on my floor. And then you're like, well, if we put a chainsaw in the hand of this robot, he technically could kill this guy, so there's a little bit of nuance. But again, whoever's doing the marketing on cobots, great job.
Killing it. Yeah. Okay.
Have you ever encountered that, like in your world, where somebody will have a very big bias for a technology, even though you're like, this is a terrible idea?
But yeah, sometimes we see that with like AMRs and AGVs and stuff like that. Like if you bound them, then you can have a machine that goes 4 meters a second, let's say. But in unconstrained fields, you have to dial them back to like 1 meter, right? So like it's a huge differential in like throughput that you can expect out of the same like capital investment. And so like we definitely do the dance all the time. Like, how fast do we want to go? How much do we want to spend? And how important is that to not have a monument built? A lot of times it turns into a huge track or monument, right? Yeah. So I think it's well taken point. So what, like for a robotic arm, what's the cost difference for a collaborative robot versus a traditional one? And what's the rate difference that I might see?
In general, depending on how you configure them, they are getting within 5-10% of each other. So they are very comparable. Yes, cost-wise.
Okay, wow. Okay.
The reason being is if you have a collaborative robot, typically the arm itself will be more expensive, but now you don't have to buy fencing and you don't have to buy light curtains.
Okay.
They're getting close. There even are some collaborative robot cells that are cheaper than traditional automation when you look at the total package. Depends on, again, weight and rate, but for sake of conversation, you could consider them the same for, the same. They're pretty good now, which is exciting because when they first came out, they were definitely more expensive, but they've gotten a lot better and they're pretty comparable.
And then rate wise, like how much of a hit would you expect to take? There's like relative terms.
Sure. I was just working on a box palletizer recently with a cobot. Their rules of thumb were like anything less than about 35 pounds and up to about 7-ish picks a minute, 7-8 depending. That includes a slip sheet. So if you have a slip sheet, that's a pick. And that's a single box pickup. So 8, 7, and about 35 pounds for a collaborative robot. For the same sort of setup, 1 in, 2 out, single box, whatever, with the end of arm tool, I would say rule of thumb, 45, 50 pounds. So you have a little bit more room there. And, something like 15 to 18 a minute, depending on pallet patterns.
So we're talking like twice the speed and more weight.
Yes. So again, it kind of depends, but the rules of thumb are you can totally do 18, 20 cases a minute with a traditional robot cell, like kind of off the shelf. So you do take a rate hit of about half. But again, if your pickler only goes 7,
it goes so fast. There's no point going any faster.
It doesn't matter. So it depends on the application, depends on how fast the upstream your pickle machine goes. I would lead you down whichever path sort of fit you best, knowing that they are almost equivalent in price, but you do take a pretty big hit on the rate.
Okay, so before we talk about future stuff, I got one other wild kind of question for you. So you kind of specialize in robotic palletizers and depalletizers, and that is largely is like there is an arm has several degrees of freedom, then it reaches out and grabs stuff like an arm does. But there's this more traditional, like an older technology, right? These unit load formers, for lack of a better word, where you have a conveyor and it slaps the boxes around into a pattern and then it just slaps it on top of a pallet and then it just makes another layer, repeats it. What's when should I consider one versus the other, or have robots come so far that like that's just a thing in the past now? Like what's the conversation there?
Sure. The gantry style or the layer robots, I mean, those have been around since I think like the 70s.
Forever. The Hobbit movie came out back then, yeah.
Older than me.
Yeah.
They are very robust. They can be very affordable. They can also fit in really tight spaces. I think like a layer palletizer or a top-down palletizer or like a gantry, sometimes we call them, those non-robotic palletizers, I think they work very, very, very well. If your actual like layers that you're forming are very simple, meaning, if you have all these boxes just lined up, like one just in a row, there's not interlocking patterns. There's just like good old fashioned column stack, right? We're going to put 4 boxes this way and 5 this way. If we have something like that where the actual pallet patterns are straightforward, if you have boxes that are very repeatable, meaning like you only have 2 pallet patterns. Let me give you an example. There is a company that makes like 80-ish% of the mozzarella cheese for pizza shops like Papa John's, Domino's,
Yep.
whatever. They just make mozzarella cheese like it's going out of style.
I love
They
the
have,
product.
yes, they're great. They have two size cases. The end. They've had it for 50 years. They have the big case and the little case. The end. It's column stacked. It comes very, very, very quickly. I think they were in the 30, 40 minute, right? They're just making mozzarella cheese like it's going out of style.
Yep.
And they have very straightforward, just, they only run one product per day. They don't do a whole lot of changeovers. I quoted a robot palletizer and also a traditional kind of gantry. The gantry actually was better for them. It was faster, it was smaller, and it was cheaper. And for them, having those degrees of freedom was actually a detriment. So they work when you have sort of a simplicity in how many products you're doing, and the pallet patterns. They work really well. I don't shy away from sort of exploring that option when I see just a textbook, very straightforward type of thing. Now, robots have gotten more common, meaning there are less providers of those gantry trains. They tend to be legacy providers, meaning they tend to have a little bit less sophistication in programming, remote monitoring, making changes on the fly. Not all of them. I'm sure there are people out there that are integrators that are really, really good. But because this technology is from the 70s, 80s, and 90s, the software tends to be a bit more dated than a robot. There's some challenges there, especially when you're trying to, like, we do robots as a service, when we're trying to make sure that we have high level crash detection, monitoring of different parts. Sometimes those gantry components simply are less tech enabled. So we can't monitor them as easily. The programming sometimes runs into challenges of making changes because it is like a CSV file that we zip into it. I know that sounds wild, but like that's the reality.
It's the 80s, Yeah.
That's the programming sometimes. There tends to be less human beings out there that know these programs, and it tends to be less visually appealing on the HMI. So there's a little bit of that, but I mean, it's outrageously an option that still exists. It's dwindling because robots are so fast and cheap now, but it's a great question.
If you find the right application, it's still a home run.
Yeah, it's still a home run. I'm sure you have some sort of legacy sort of like conveyor technology that you use that, has been around since the 70s and 80s that sometimes is the right choice.
Yeah, absolutely. There's all we still use shoe sorters, right?
There we go.
They're not new. They're fast, right?
They're not new. Yeah. They push a box real good, when the rate and the time is fine. So
absolutely. Okay. So let's shift gears a little bit and talk about some future stuff. So like try to predict the future a little bit, and then let's try to hit, get your crystal ball. Let's try to hit some stuff like, mixed pallet build. So like this is like, I think on the hard end of, palletizing. So what does that look like? And then like, where are you guys slotting in, or where do you see like AI helping out and like the super advanced vision stuff? Really, I think is probably what I'm asking there. Yeah. So like talk to me about these kind of topics.
All right. I was explaining this to someone the other day. So with non-tech, so like not vision enabled, not AI enabled palletizing, you need to tell the robot, this is what we're doing, and we have to do that, right? So at your pickle company, you have to tell the robot, we are doing the small pickle boxes.
In this recipe pattern.
In this recipe that is it's set. It is set in stone. And that's cool and fine if you make small pickles and big pickles, right? It's no big deal.
Absolutely.
Kind of where we're sort of sitting on in the robot world is being able to handle variation. So one of the easiest things you can feel is trailer unloading. So knock, 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 Mr. Trucker is here. He's got a fluid loaded trailer, right? So boxes stacked in
this
all
is
sorts
a
of configuration.
hot topic right now. Yeah,
Yes.
everybody's trying to do this.
Right. Knock, knock, knock. Your container is here from China. It is fluid loaded. You have, 27 different box sizes in an infinite configuration because some humans somewhere else have put as many boxes as they possibly can. So you're here and you're like, okay, might as well just get like 7 dudes and we are going to unload this trailer one by one.
Boxes. Yep.
Take a box off, put it on a conveyor behind me, and that conveyor goes and does stuff. So that job kind of sucks, right? It's a lot of torsion, it's hot, it's terrible, it's not fun.
Yeah, nobody wants to do it. It's time consuming too, right? It takes a lot of people.
It's mind-numbingly boring. It's like stunningly boring, right? So let's throw a robot at it. Okay, let's try to do this. So now imagine yourself as a robot. So first you're blind, so we got to make you see. So we have to throw some cameras on you, right? Now, we have a camera on you and you need to be able to identify the different boxes in their Lego configuration. Whew, that is a lot of processing. Do we use edge detection? How are we using this camera to make sure that we know this is a box, it's on the top right, and it's 20 inches by 17 inches? This is where AI comes into play a lot because, in industrial applications, AI is just how can we process large amounts of data quickly and repeatably? How can we train something to learn faster, right? How can we take bajillion images of boxes and be able to parse down, okay, that's 17 by 20 inches, that's sitting there. So once we enable the robot to see the Lego configuration, right, using vision and AI, cameras are getting real good and cheap. We've got insane cameras on the iPhone. Remember our 3 megapixel cameras from the 2000s where we're like, I'm going to upload these on Shutterfly. And it was blurry and terrible, right?
You got to take the card out, put it in your computer and upload it to MySpace, 100%.
we have lenses. We have image processing that can go very fast. We throw a little AI on it, right? So we're taking millions of photos of different angles of inside of a trailer that's being unloaded. Once we accomplish that, then now we have to say, okay, I see the Lego pieces, I see the boxes. Now I have to tell my robot arm, please go here, use your hand, right? Your end of arm tool. And you have to grab that very precisely without knocking everything else and not damaging this box and taking it back to a conveyor. So I think that coordinating that conversation of what me and you as humans do in a moment, right?
Our brains it's trivial. Yeah. For people.
Trivial. Mm-hmm. You could take a 6-year-old and say, hey, take these boxes, from Christmas down and put them, somewhere else. Mm-hmm. It actually takes quite a lot of computing up here. How do we trade a machine to do that? So the trailer unloading problem is huge because into your systems, that's probably a huge bottleneck, right?
Yeah. Well, yeah. So we have all these traditional conveyor unload. We put a flex conveyor or we put a CalGen unit in there or destuff it, right? We try to make it as comfortable for the person as possible. Mm-hmm. But really what we're doing is we're making it a very boring, hard job comfortable. It's we haven't cracked the code yet. And I think that we're very close as an industry.
There are quite a few robotic outfits that are tackling this problem of vision, AI, and how do we translate that into repeatable robot arm action? Mm-hmm. There's probably 4 or 5 sort of, at least in the United States, that are doing proof of concepts, have actual machines out there.
I think Picklebot is actually the name of one. Yeah.
Pickle's one of them. I think Dexterity is also one of them.
Didn't Boston have one as well that they're working on?
Boston has one that they're working on. There's a couple more inside of the larger system integrator space. I know Bastion has one, maybe. Yeah. Everyone's trying to chop at this. And with the rise of cheap vision and I want to say cheap processing power, but cheap processing power and trainable algorithms. So that's AI enabled stuff. that is where you're starting to sort of get over that hump of how do I identify the boxes and take them off very quickly. Some people have tried to do it mechanically. Like there's some old school patents out there where you have the container and then they're like, you just tip it. And then like we control the fall and singulate them out. Like that's
a controlled tumbling. Yeah. So there's some singulators actually on the market that work with sort of the same principle. And it's always a conversation, like with like every time we do a whole solution, it's this, well, let's automate the trailer unload because that job obviously looks super easy. But again, for all the reasons you've just said, like this is the last tough nut to crack in most modern distribution centers. Yeah.
And so AI is tackling that random, depalletizing, trailer unloading. Depalletizing is a sort of easier version of trailer unloading. Trailer unloading is, they're similar, right? So we're looking at something random. We don't know. We have to identify it and then we have to pick it up. Depalletizing is a little easier because we only have to do it a pallet at a time. Trailer unloading is more complex because we have to do a trailer and there's like a whole level of depth that is much more difficult. So I think depalletizing is further along than trailer unloading, but they're sisters, right? They're similar. Once you can kind of get one, but it's really that question of vision and AI. How fast and how quickly can it do it repeatedly? So that's kind of what's happening right now.
What about pallet builds, a mixed pallet build? Like this is the it's the other end of most buildings, right? So I've sorted all this order and I've got like this random assortment of boxes. They're not all the same size. And actually humans even still struggle with making pallets like a good pallet. You'll hear supervisors say, "Oh, this is a bad pallet." What's bad about it? Like it's a qualitative problem, right?
You have we'll call it like rainbow pallet or mixed pallet building. It's of a similar vein as depalletizing. You have a couple of advantages that make it sometimes a little easier. One, you tend to have more time to process, meaning if we can like Cubiscan, which is like a proven technology, right? If something's coming at me singulated, I actually have the luxury of knowing like it's, 10 by 10 by 10 and it's coming down.
32 pounds.
And it's 32 pounds. We can use, a check weigher that we've had around for, again, like the 70s.
Dim weight scan technology is, locked in.
And that can transmit very quickly. So then at least we can sort of, tell the robot, hey, you don't have to do this with vision. We're going to tell you, we're going to give you the answer. It's kind of like taking a test and like somebody's like, I'm going to give you, I'm going to give you part of the answer.
It's C.
Yeah, it's C, right? Yeah. You have a hint, right? You already have a hint. So we know if it's 10 by 10 by 10, which is a terrible box to palletize, but whatever. Coming down the line, right? And it's 32 pounds. Okay, great. So now the sort of the algorithm, the AI, the computing, the intelligence that I'm doing is not the seeing part, but the putting part, right? So it's like knowing that I have these things coming on deck. Do I know 3 of them? Do I know 2 of them? Do I know 1 of them? We have to figure out how do I build, right, the pallet. So that's you get the answer on what's coming to you, but you still have the conundrum that a human struggles with is how do I put these boxes on this pallet not knowing what's going to come next? It's the Tetris problem.
Yeah.
You're playing Tetris. Yeah.
You only know one weird shape ahead.
Yeah.
Right?
So you think
and you can get it wrong.
This long skinny one here, and then you're like, oh, well,
I got another T-shaped one. Great.
Yeah, great.
And another T. Yeah.
Yeah, so it's the Tetris problem. So that part people are decently good at because you have that extra advantage of knowing what's coming. Okay. So that's good.
All right. Sick.
Yeah, that's my kind of my opinion. What do you like? What have you? I know we're at that time, but I'm saying it back to you from your end. What these are all coming from the robot perspective. What's the most pressing issue when it comes to total warehouse solutions, your automation.
It's really that. So getting it off of the truck and getting it built into a pallet or getting it onto the truck, like those are the areas where there's not like solid solutions today. So everything else in the building, I can look at an array of technology and I can evaluate which one's the right investment, right? And which one's going to be the best fit for this operation and all their data, right? Like, because oftentimes I'll help a customer, I'll look at their inventory snapshots, I'll look at their order mix, I'll look at their item masters and like understand all this stuff and everything between the doors. Like there's a plethora of solutions, right? I can go robotic here. I can go mechatronic here. I can just use some traditional conveyor, or maybe it's like, powered industrial trucks, right? There's a way to figure all that out. But once it gets to a door, like everybody just kind of doing this, right? And then you'll see like the least amount of automation, like in the entire, you'll walk through a building that's got millions of dollars of automation. You get to the door and you're like, okay, well, there's some guys throwing boxes in there. And that's probably the biggest like conversation we end up having when we go through solutions. Like I think once that dam breaks, and it sounds like it's very, very close, right? Like all the stars are aligning, like then it's gonna be wild. We'll start seeing lights out buildings, I think, once that happens.
Yeah. I mean, I think there's always going to be a couple of humans around, but yeah. It's so interesting that the ins and the outs, which are so important for the performance of the system, are they're in the dark ages. They're still just like dudes throwing boxes.